So I just, yeah, do you think that we passing this on to the listeners of the difference? Because that's what we do it for the
Hey, how are you doing? It was awesome. It was really great. We left around 8, so yeah, it was nice. Traffic was easy. Coming back was long, but it was fine. It was really pretty amazing place, and it's amazing that it's right here. That's incredible. Yeah, yeah. Yeah, yeah.
Somebody got two-wheeler towards the housing segment easier than it. I think of that. Maybe she didn't know.
Always hard to give a talk on these double screen things. Nobody likes it. It's funny. I guess for students it must be good in a class, but yeah. Oh, you use that? Yeah, my problem is when I use the iPad, I talk to my computer instead of talking to the audience. Really? Yeah. Okay. Interesting. I see. Yeah. Okay. Yeah. So you're used to it then. Yeah. Okay. I see. Right. Right. Yeah. 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 Cool. Yeah.
I don't know. For the most part, I'm probably only one in organic chemistry.
Yeah. So your niche is good.
You probably say, hopefully technology will go level. There I give you a presentation like I'm with GPD prediction.
Right. Yeah.
All the
That would be good. Yeah.
ऑनलाइन है तो आज इनसे मेरी बात हुई थी मैंने उनका मैसेज किए थे वो वीडियो या फोटोज
Past few days, the screen, people's slides got compressed this way and elongated that way. We spent like 20 for my talk figuring out how to make it normal. So it was not easy on that projector. So, I see. Yeah. Somehow I heard. Yeah. Right. Yeah. But I did yeah.
Why didn't I reach here?
I see. Yeah. That's funny. Yeah. Well, we did eventually figure it out, but it was, I think I was the only one who gave the talk that way. Everybody else just didn't seem to care. But I was like, no, what? But this one just automatically fixed it for the right side. But it's a shame it's cut off. Our projectors do that too. It's kind of strange. I don't understand why that happens, but I mean, yeah. I don't think I'll ever change. I hate this. Yeah. I'm telling you. That's very funny. Yeah. Yeah, my students know for sure.
So now what I buy, and then I make
Yeah. I make them. Before they give a talk, they have to print out all their slides and hand them to me, and I hand write on them what I want changed and give them back, and then they have to make the change and they know that if the slide has like big even spaces on it, that I just write the word ugly in the middle of the thing. So that's it. It just means this is ugly. Make it look nice.
And this.
Yeah, right. That's ugly. That would get an ugly out of me. Yeah. Yeah. So here's one thing though. I wonder what you think of this. So what do you think about from one slide to the next slide? To the structure. So on each slide, the structures have to be the same size. For sure. But how about from one slide to the next slide? Does it matter? Is they're identical in size?
Yes, they have to.
Okay, all right. See, I differ there. To me, it's like each slide is its own piece of art.
Okay.
And I don't care as long as on the slide everything is consistent. It shouldn't be wildly different, but I don't mind if they're different size a little bit. Yeah.
They can
Yeah. That's right. Ours is not. Look, we use a different style for our papers. Yeah. So, but you should think about it. It's from one to the next. The audience doesn't remember what was on the last slide. So if you need to expand the size of, the page, it's like it doesn't so much matter. But you'll see on my slides, they're not all the same from one to the next. Yeah. But some of my students agree with you, but I tell them it doesn't really matter. But in a paper, it matters. Yeah. But now Jax doesn't seem to keep the things the same size. It's so weird.
Yeah.
They'll expand the size of the. And I look at the paper, I'm like, that structure and that structure are different sizes. They're on the same page. This is ridiculous.
Yeah. It's just totally producing much better.
I know. Yeah.
And trying to mess with.
Oh yeah. Well, I'm editor of tetrahedrons, and we're the worst. I mean, our page layout people are absolutely terrible. So, but that's a different division. It's like big.
Kavita Dasaka, feel privileged to welcome you all to the third Professor G.K. Trivedi Annual Award Lecture 2024. We are honored here to have Professor Brian Stoltz, one of the eminent researchers in the field of total synthesis from the California Institute of Technology. Welcome, Professor. It is euphoric to have you here.
It's my pleasure.
I now request Professor R.B. Sunoj, Acting Head of Department, Chemistry, to enlighten us about today's session.
Since I'm acting, I think I can afford to act. Welcome all of you to this important organic chemistry lecture series in honor of Professor G.K. Trivedi. I've known him for many years. Even after his retirement, he used to be very regular visiting our department, and we used to discuss a lot of science. In the corridors, sometimes in offices, he has been very active in engaging in constructive discussions on any topic related to organic, including physical organic, where I have a lot of interest in. In regards to the lecture series, it was due to the generous support by many of his own former students, PhDs, master students, as well as postdocs, who instituted an endowment, and Institute has a very well-oiled machinery to institute such endowment lectures, and we received decent contribution, support from alumni, and that resulted in an endowment fund through which we could afford to invite eminent speakers. And I'm also very proud to share with you that the previous speakers in this series, GKT lecture series, was Dr. Trivedi Chandrasekhar, and then followed by Professor Eric Carrera, and today we have another eminent speaker, Brian Stoltz, whose work, of course, I have read, particularly on quaternary stereogenic centers, and I've cited many of his papers because we have some interest in mechanistic aspects of that. So with that, let me also give you a brief note about Professor Trivedi's association with the department. He started his career here in chemistry department in its formative years back in 1966 and stayed through all the way till 2002 when he retired. And he maintained association, as I was mentioning before. He has a long list of students who graduated with him, around 50 PhDs, 45 PhDs to be precise, and 50 master's students. And a lot of them keep in touch with him. And they have even formed a GK Trivedi Parivar, which in Hindi means, Parivar means family. So people have very good association with him, maintained all the way through. So it is a great pleasure to institute something in his honor. And a couple of other details that he has been a prolific publisher. Back in the days when facilities in the department, I mentioned formative years, was very limited, still he managed to publish 160 research papers, which is remarkable given those constraints back in those days. In addition, he was always known as an excellent teacher, and I have the primary evidence for that. Whenever I talked to him, he was so clear, so crisp in explaining details. So he was also awarded with the Excellence in Teaching Award of IIT Bombay. And these, I'm not surprised at all, a great researcher, very good teacher, very good human being interacting with colleagues and students. And that is precisely the reason for his students coming together and instituting something of this sort, where we could invite eminent speakers for GKT lecture. That's the introductory note which I wish to share with you. Thank you.
Thank you, Professor Suloj. I would now request Professor Nandita Madhavan to deliver Professor G.K. Trivedi's message on his behalf.
So Professor Trivedi would have liked to be here, but it's difficult for him to travel currently. So he sends his message to everyone. Personally, for me, Professor Trivedi's lab was the first lab where I got a flavor of research during my MSc project. The first column, the first reaction setup, it was really enriching. And for those, like Sunoj said earlier, he's a very passionate teacher. So when you speak to him about chemistry, you can literally see his eyes twinkle. So you have to see this to believe it. So I'll just read out the message that Professor Trivedi has shared. Warm greetings to all present here for the third GKT lecture. I wish to thank the head of the department for organizing this event, the committee for inviting Professor Stoltz, a very distinguished synthetic chemist, who will be speaking on the total synthesis of complex alkaloids, which is a topic of great interest and passion to me. I thank Professor Stoltz for graciously accepting the invitation. I'm looking forward to hearing the talk online. The department faculty and staff have always been very warm and collegial. I extend my heartfelt greetings to all. My students have been an energizing force for me, and I'm so happy that they instituted this lecture. I hope the talks from distinguished speakers like Professor Stoltz is a source of motivation for the new generation of IITB students and budding synthetic chemists. So wishing you all the very best. Thank you from Professor Trivedi.
Thank you, Professor Madhavan. I now request Professor Santosh Gharpure to illuminate us about our today's distinguished speaker, Professor Brian Stoltz.
Thank you. It's a particular pleasure for me to introduce today's speaker for this GKT award lecture. Again, before I introduce the speaker, let me say my two words about Professor Trivedi. He was one of the inspirations for me to take up organic synthesis. And this kind of award series, which his students have started, who allows us to bring people of the stature that they are, I'm sure they will continue the legacy of inspiring generation of students to take up organic chemistry, organic synthesis in particular, a subject domain which was Professor Trivedi's passion, continues to some of us, and hopefully it will continue to the next generation. That baton will be passed through his exciting lectures that we are getting to hear, thanks to his students who have instituted this award lecture. Today's speaker is Professor Brian M. Stoltz. Brian was born in Philadelphia, Pennsylvania. He attended Indiana University, where I also attended Indiana University, but we were in different places. I was in Bloomington, he was at Pennsylvania. So I see that we seem to be having more than a connection there. We have been talking about certain things, similarities. Interestingly, what I learned is that apart from chemistry, or before he took passion to chemistry, he was excited about music and mathematics. But then, like many of us, he fell in love with organic chemistry, thanks to another inspiring teacher, researcher, Professor John T. Wood. Following year, he worked abroad, crossing the Atlantic, I believe in Bayer AG in Germany, and then Ludwig Maximilians Universität in Munich. He earned a dual BS in chemistry and BA in German in 1993 from IUP. After completion of his undergraduate studies, he went to Yale University, worked with Professor John L. Wood. While at Yale, Brian worked on total synthesis of indolocarbazoles, long list. I'm not going to bother you with the names, but very, very interesting molecules in their own right. After completing PhD, Brian moved to Harvard to work with Nobel laureate Professor E.J. Corey. And there he developed enantioselective route to nicardrenone natural products. Then he moved to Caltech, started his independent career there, and he has been there ever since. Now as a professor of chemistry and Heritage Medical Research Institute investigator. His research group studies the design and development of new strategies in complex molecule synthesis, development of methodologies. He did talk about some part of the method story in the previous talk. Today, I believe he's going to be talking to us on the total synthesis part of his research. He's very, very well decorated scientist, and if I were to read the long list that is there in front of me, probably I will give his lecture time, basically. So I just mentioned a couple of the relatively recent ones. He's fellow of the American Chemical Society. He's a Chemical Society Review guest editor, co-editor for New Directions in Natural Product Synthesis. American Chemical Society Award for creative work in synthetic organic chemistry, and I'm sure this particular award you will see why they chose him particularly for awards of this type in today's talk as well. So I'll skip the long list in the interest of time, and without further ado, I invite Professor Brian M. Stoltz to give this award lecture.
Well, turn this on.
He has.
Okay.
He has.
Well, thank you so much for the really kind introduction. I want to start just by thanking everybody here at IIT Bombay for the kind invitation to be here, and of course the great honor of being part of this Trivedi lecture series. I hope that Professor Trivedi is watching online. Thank you, sir. I wish I would have had the chance to have met you. Certainly, papers coming out of the Trivedi group were things that we watched, certainly through graduate school. I remember, 5+2 cycle edition chemistry coming out of the group, probably performed by some of the people in the Trivedi lab. So thanks to them for the organizing the series. I think that's a great honor, really, to your teacher and mentor. Maybe he's something of a guru, I guess. So it's something that I think we as academics all aspire to, that our students, have the same kind of affection that clearly the Trivedi group does for their advisors. So it's a great honor to be here. And I especially want to thank Professor Kaliappan also for the invitation directly to come to both the previous meeting and to this event. And I also want to particularly thank his student, Garov, who's just been an amazing host and shepherd of me. He grew up in a village herding goats, and so that was me this week. So thank you very much for that. It's been really terrific to get to know you, and I wish you all the best of luck as you move forward in your career. Okay, so today I'm going to tell you about a story in complex alkaloid synthesis, and it is going to be a relatively long story. I hope I'm going to be on time. Actually, I'm going to watch my clock here just so that I'm not super duper long. But it's a long story because it takes place over really almost the span of my career. So anybody who was at the talk the other day knows that that's the kind of story I actually like to tell. That story the other day also spanned a long period of time in my group. So of course there are many players that are a part of that discussion. And so shown here are some of the major players of the work I'll talk about today, sort of shown on the periphery. And you can see it goes all the way back to even the very first class of students that I had in my lab, including this guy. This is Uttam Tambar, who I think has visited this department in the past. Uttam was one of my favorite students of all time. Don't tell my other students that, but he, you'll see in the course of this talk, some creativity that he brought to our group that we're indebted to him for. But really early people in the lab like Eric Ashley, this guy Kevin Allen, and then students and postdocs that came much later and much more recently, people like Eric Welling, who's a great postdoc in the last few years, and Pha Namnithapon, who is a terrific graduate student from Thailand. So anyway, I'm indebted to the entire group of folks here, and you'll see their names on the slides as I go through today, the talk. But I want to start with a little bit of an overview of kind of how we think about science in my group. Primarily as a graduate student and a postdoc, I worked on complex molecule syntheses. And so I think to the outside world, people thought of me, particularly when I interviewed for positions and maybe even still to today, as someone who works on total synthesis. That was really what I was known for. But in every one of the syntheses I ever worked on as a student or a postdoc, we had to develop new chemistry in order to overcome synthetic challenges that amounted in the course of those endeavors. And so I felt like most of my career I was developing methods and then using those methods that I was developing to solve the problem that they were inspired by. And so that seemed like a reasonable approach to science. And so that's how we do things in my group. We start projects on the left-hand side of the slide, thinking about molecules that we think are going to push the limits of complex molecule synthesis and push the limits and the frontiers of our science. We look at those molecules, we think about different ways that we can make them, try to come up with and devise unique strategies that are both effective and concise, but invariably, because we've chosen targets that push the limits of what we know how to do, we have to invent something new. And that's the whole point of what we're trying to do, is we're using those targets to drive developments in our science of synthesis. So we very quickly move from these complex structures to the central part of the slide, which honestly is probably the central endeavor of our lab, is to try to develop new methods that help us overcome challenges that we've identified because of the complex molecule. So the structure drives the methods development. We spend a lot of time trying to build methods that then allow us to overcome those. We move back to the targets and apply those methods in exactly the scenario for which they were invented. But of course, when you have a new method in hand, you can do anything you want with it. And so we often then go off and find other targets that we can investigate. And these targets are largely identified for the fact that we think we can use our method to overcome some synthetic hurdle over existing technologies toward their synthesis. But if these molecules are chosen from the same subset of molecules as the ones on the left, these molecules will then also inspire new methods because there'll be aspects of the synthesis that we again don't know how to overcome. So that feeds back into the methods development section again. So we call this approach a target-driven methods development approach. And you can imagine that there's a kind of feedback that occurs between the complex molecules and the methods that are then developed and vice versa. And this seems like a very neat and tidy, organized path for science. But we all know that science is not organized and neat and tidy, and it can be chaotic. And this is really representative of the true story that happens in the group. That there are connections that get made between these projects that you never could have designed. a priori. They come about because of those creative students that I showed on the first slide talking to each other. And two students who have nothing in common other than they're in the lab and working on chemistry will come up with a new project that links their projects together in ways that you never could have imagined. And for me, that's the truly exciting aspect of what we do. That you can, instead of a 1 + 1 = 2 kind of approach, a linear trajectory to science, this sort of chaotic environment allows us to have a very nonlinear approach, a kind of 1 + 1 = 7. Right? It's a nonlinear effect, these students' creativity. And that for me is really the fun. What I have to do is make sure that we don't go off the rails, that we don't go, and start investigating things that really make no sense for our group. So we have some overarching principles that we try to keep in mind. So when we're thinking about synthesis, we're really trying to develop new strategies and tactics that allow us to access something that's very complicated and has some function. That's typically, that's really typically all that we look for in a synthetic study. In our methods development, and you saw a little bit about this the other day, what we're really trying to do is enabling chemistry for other people to use, right? So I tell my students that, with multi-step synthesis, it's great to put a compound into a bottle, right? You finish a synthesis, it feels great, it's a terrific goal that you've met. But what we're trying to do on the methods side of things is actually enable other people to put a lot of compounds in a lot of bottles. And if you can do that, then you've successfully developed a method that has some breadth and some importance. And then the last overarching idea is that, is related to just discovery. We're in an academic setting, and the hope is that we're going to, exploit or uncover or discover something that's really fundamentally new, right? Trying to change textbooks, put something that we didn't know before into what we now understand about chemistry. And so students often will forget that this is available to them in an academic setting. That students are very driven to the finish line, thinking about the PhD and thinking about how they can write their thesis. And they like it to believe that it's a linear path to the PhD. But I think the most exciting PhDs are the ones that follow a very nonlinear path, right? Where you're constantly turning and twisting and uncovering new things and following up on them and digging deeper. And you never really know where you're going to end up. This is supposed to be an adventure. And so that's what I have to remind them of that as we go. So these are kind of the overarching principles of the group. I won't mention them again, but you can keep them maybe in the back of your mind as we go through today's talk. So the story I'm going to tell you revolves around this family of molecules called the tetrahydroisoquinoline anti-tumor antibiotics. This is a very broad class of natural products. There's many more than 60 known. This is an old slide. There's probably hundreds known at this point. They're biosynthesized by amino acid condensations, and you might be able to imagine some of that as we go through. Generally speaking, they're broad-spectrum antibiotics, but they're not good antibiotics because they're too toxic. In fact, these compounds are typically covalent modifiers of biological nucleophiles, and the warhead of these molecules is in this amino portion of the molecule here, where this X group, which either is typically a hydroxy group, some kind of an ether linkage, or a cyano group, gets expelled in the biological setting, generates a very reactive iminium ion, and then that traps a biological nucleophile. So what they're really better at is being cytotoxic agents, and in some cases cytostatic agents for anti-cancer therapies. And in fact, this molecule, actinocytin 743, is used clinically for certain solid tumors. So that's really the sort of hallmark member of this class of compounds. It is the most complicated molecule. And I won't talk about any attempts at the synthesis. We've never even tried to build this molecule. But this is the molecule that's used clinically. But this family of molecules typically comes in two very broad types. One of them is exemplified, say, by cyanocycline and quinacarsin and lamotamycin. And that's the case where we have a single tetrahydroisoquinoline unit, either as that aromatized benzenoid structure or the oxidized quinone type structure. And it has a single tetrahydroisoquinoline unit, and it has a 2-carbon bridge in this diazobicyclic unit. So you can see that very clearly in lamotamycin and quinacarsin. In cyanocycline, actually the 2-carbon bridge is here. It's drawn a little bit less suggestively. The second class of molecules actually has two tetrahydroisoquinolines. It has this one on the left that's very easy to see, like this one and that one in actinocytin and geromycin. But it has a second one that's part of this bridged bicycle. So now instead of a 2-carbon bridge, it now has a 3-carbon bridge, and that 3-carbon bridge shares another aromatic or quinone type structure there. And in the particular case of actinocytin 743, it actually has a third tetrahydroisoquinoline that loops between these two positions. So our endeavors in this area started with one of these mono tetrahydroisoquinoline anti-tumor compounds called lemonomycin. So lemonomycin itself had a really interesting story. It was isolated in 1964. It was shown to have broad-spectrum antibiotic activity at the time, but was an unknown structure. They didn't actually elucidate the structure until sometime later. And at the time, it was found to be a relative of those molecules I showed on the first slide. But it turns out it was the only member, and remains the only member of this entire class that has been glycosylated. So we thought that was kind of an interesting and unusual structural feature of this particular molecule. That was one of the reasons we were drawn to this structure. And its structure had only been elucidated some years before we started at Caltech. So there were no approaches, even in the literature, toward this compound. Of course, it has all of the same synthetic challenges that a typical member of this family has. It has this diazobicyclic core structure here. In this particular case, again, it has this dideoxyamino sugar that was essentially a very unknown sugar in the literature. I think there was one other example in a natural product possessing that particular sugar or pyranose. It has 10 stereogenic centers, 3 nitrogen atoms, and of course, many of these functionalities you can imagine are quite sensitive. Right? And that is the trick in multi-step synthesis. You know that the final compound has some thermodynamic stability, but you really don't know about the intermediates as you get close, whether or not those compounds are going to have stability or not. We all have encountered this. Anybody who's ever done multi-step synthesis, you get some complex molecule, you subject it to some relatively mundane set of conditions, and you end up with nothing. It all decomposes somehow. And it's because of all of these, cross-reactive functionalities that are present in these molecules that lead to really unpredicted, and in many cases I would say unpredictable, kinds of reactivity. And that, I think, is one of the challenges of multi-step synthesis. So our main design for this was to think about this glycosylated unit as not an afterthought for synthesis, but to actually design the synthesis with that particular structure in mind, right? Most people, I think, would look at this and disconnect the molecule here and cleave the sugar away. We didn't want to do that. We wanted to incorporate it as part of the route. And so instead, we cut out this carbon at this position through a Pictet-Spengler retrosynthetic step. So that takes us back to an aldehyde that's already been glycosylated, and this remainder of the structure that has the diazobicycle and an aromatic surrogate for the quinone in the form of a lactam. This compound, then, we decided we would disconnect through a carbon-carbon bond linkage to this iodo enamide and this boronic ester. So that was our retrosynthesis of this molecule. So the diazobicycle, we decided we could generate through what's called a Joule-Garner cycle addition. So this is a variant, of the Trivedi cycle additions, dipolar cycle addition. In this case, it's a 3+2 dipolar cycle addition, depending on how you count. And we used an Alkaloids or Stoltz derived acrylamide in that cycle addition. And that controls the facial bias of this 3+2 dipolar cycle addition to a large extent. Upon completion of the reaction, we simply work it up with sodium borohydride. That reductively cleaves away the Alkaloids or Stoltz and leaves us with a primary alcohol, and that molecule now has 94% EE. So we just do that all in one reaction sequence. We TIPS protected that alcohol and then iodinated the olefin with high selectivity, it turned out, and then subjected that to a palladium catalyzed cross coupling, just a Suzuki reaction, to access this enamide. Okay, so that structure then we had in hand relatively quickly. This hydrogenation of that olefin, however, turned out to be extremely difficult. right? And so we needed really forcing conditions for this. And actually that particular olefin in other people's routes has been a challenge for this synthesis in this scaffold. In any event, at 1,000 psi with palladium on carbon and a mixture of ethanol and trifluoroacetic acid, we could actually obtain this, this product as a single diastereomer and 71% yield. And that was great, and that set us up for this Pictet-Spengler process. That, however, did not work. Right? So there are some Pictet-Spengler type reactions where you can form in situ an acyl-aminium ion, and that's what we would have to do. We were trying to engage this amide, this lactam, with our aldehyde to form an aminium ion that would then cyclize. That never worked in our system shown here. We were never able to observe that. And so we took then an alternative route where we had to concede that that was not going to work. And so instead of that, we decided to reductively open that ring to generate this amino triol system here. And we do that by first CBZ protecting on the amine out here of our diazobicycle. We cleave with potassium TMS, we cleave this tosyl group down here that we had on this molecule just as part of the synthesis of the boronic ester, and then we bis-Bach protected that intermediate, and then exhaustively reduced that and acetylated worked this up with acid to then cleave the TIPS group at the end. So that leads to this amino triol compound, and that now, as a primary amine, should be a competent amine for the Pictet-Spengler reaction, and indeed it was. So just treating this amine with the aldehyde that has the limonamycin amino sugar embedded, that undergoes a very effective Pictet-Spengler reaction that produces a tetrahydrous equivalent of a single diastereomer. And this is actually very well known in this field. So many other people have used Pictet-Spengler chemistry to build these tetrahydrous equivalents in this natural product class. So this was really using other people's methods to build this structure. That worked just fine. We could take that compound. We're left with 3 operations. Effectively, what we needed to do to go from here to here was oxidize in the first ring up to the quinone. We needed to deprotect our CBZ group. We needed to oxidize this primary alcohol to an aldehyde oxidation level. The natural product actually exists as a hydrate. That's why it's drawn in this way, so it's really an aldehyde. And we needed to oxidize this other primary alcohol, again, to an aldehyde that would then clamp shut to the amino carbonyl amine structure shown here. So those were the operations we needed, essentially one reduction and then oxidations. We didn't know the order, and actually in this Strategies and Tactics book chapter, we describe all of the possible permutations. The one that was successful was the last possible chance, and it actually was the one that worked, which was to reduce first, so we hydrogenalized the CBZ group with hydrogen and palladium on carbon. We then Swern oxidized both primary alcohols, and then a can oxidation in the final step oxidizes this to the quinones and completed the synthesis of limonamycin. So this was the first synthesis that was great. It was actually I think our lab's first synthesis, or close to it. So in the end, it was a 15-step synthesis, pretty rapid construction of the framework. We were able to build at least most of the carbon-carbon bonds very rapidly. And we were successful in directly installing this glycosylated unit, not as an afterthought, but really as part of the synthesis. So those were the upsides. Those were the good things. The downsides, I would say that the isoequivalent unit itself, of course, we made in a stepwise way, right? We had to build one bond with Suzuki and another bond with Pictet-Spengler. And the Pictet-Spengler cost us a number of steps because we couldn't use the lactam directly. We had to go through this reduction and then reoxidation sequence. And that really increased the step count of our synthesis overall. Still not terrible, but it increased it. From my standpoint, we also didn't have to invent any new chemistry here, right? So we published this paper in 2003. It was a great paper, and we were all very excited about it. But in many ways, this represented a dead end for the lab. This was the end of the story. We made the molecule and moved on. Okay, so now keep in mind this chaotic picture that I mentioned, right? So the students who are working on this project, they're talking to students who aren't. There are other things going on in the lab. The project I talked about the other day was taking off in the group. And so we were actually thinking about building quaternary centers. None of these molecules have quaternary centers in them, the molecules that I'm talking about today. But in the lab, quaternary centers were something that we were thinking about a lot in the group at that time. And that project was just starting. And so enter Uttam, who I mentioned in the introduction. So Uttam was a struggling third-year graduate student at the time. He would admit that, I think, to all of you. His chemistry wasn't going well. He got off to a great start, and because of a quaternary center, we couldn't finish the synthesis that he worked on, despite they tried. He and a postdoc tried for about a year and a half to build one quat center by a methylation. That is the only thing missing from his natural product was a methylation, and we never finished the compound. So Uttam was frustrated, but he was an incredibly creative scientist. And at some point, he came into my office and said, I have an idea for building a quat center. What do you think? And he drew this structure, this reaction on the board. The idea was he was going to try to complex an enolate, a stabilized enolate of, say, an acetoacetate type unit by some kind of a metal center that had some chiral ligand framework, and he was going to aerolate that. There were some projects in the lab for which we needed benzylic quaternary centers, and he knew that, so he was talking to people and came up with this idea. And instead of doing something that at the time would have been very common, which would have been, say, a palladium-catalyzed alpha aerolation reaction, he decided to do something really different because he was reading the literature and thinking about other kinds of chemistry. He drew benzene on the blackboard and said, what if we use benzene? It's an unusual but very reactive electrophile. We're just going to template this enolate and throw this electrophile at it, and it should work. Sounded like a great idea. The only trouble, I guess, with the idea was that there were no examples of this reaction in the literature with or without any sort of templating metal. Just the bond construction was unknown. And so we thought, okay, well, let's just see if we can get this reaction to work. We had never touched a benzene ever in our group, at least not knowingly. Maybe we made them unknowingly, but so we thought we'd get our feet wet with just a practice reaction. So we decided we would generate the benzene through this famous Kobayashi elimination. We thought for long term this would be, probably the mildest way to generate these kinds of compounds. And we're going to use this 1,3 dicarbonyl in the presence of cesium fluoride. Cesium fluoride should be basic enough to deprotonate this, and then off goes the reaction. So if the cesium enolate reacts with the benzene, we envisioned that we would get that aerolation event, and then this phenylalanine should find a proton from somewhere, maybe another molecule starting material, maybe an acetonitrile molecule, but it's a very reactive phenylalanine. It should find a proton and give us the product. Okay, so that was the design. Uttam performed the experiment and did indeed observe some of that product. But as you can see, it was the minor product of a two-product mixture, with this other product being the major product. So, okay, that was a confusing product for a while until we drew out this mechanism and said, well, okay, well, maybe this phenylalanine is slow to protonate and instead adds into this carbonyl that's been forms this benzocyclobutene that then fragments through a retroaldol process from the cesium alkoxide, breaking this internal bond and leading to this product. And so that seemed like a really interesting reaction. And now remember, Uttam's a third-year grad student, has no papers. He's thinking, how do I graduate? I need a thesis at some point. And so at that point in time, this very unusual and pretty novel kind of pathway seemed very appealing. Right? Whereas this one was the minor part of this two-component mixture. Even though that was the goal of the project, we decided to shift gears and focus on this unusual product, which we thought of as a kind of insertion process. It's really a carbon-carbon insertion process on a benzene to form this kind of a product. Really an unusual thing. If you think about retrosynthesis of a molecule like that, you typically wouldn't think about breaking both carbon-carbon bonds at once and reconnecting them in your starting material. So it's a really unusual step. We were excited about it. So we left this behind and we decided to focus on this. So I should say that I'm actually happy that we stopped working on it, because it took another student in the lab, now working independently, a student, Neil Gard, who was in the lab at the time and knew all about this project. It took him 18 years or something, 15 years, to finally solve the problem. They went off and did it themselves, using chiral auxiliary chemistry on an enamine like this to generate these alpha arylated 1,3 dicarbonyls. So we never did another reaction, but eventually the problem has been solved, which is great. But we'll go back in time then to Uttam in 2003 or so. And what we found was that this chemistry is actually pretty general. Actually, the modest yield that we had seen for that product, we could overcome that by just removing the methyl group at the central carbon. Remember, the methyl was there because we were hoping to make a quat center. We don't need a quat center in this case, so if we remove that, now the reaction goes to 90% yield. And we call this an acyl-alkylation reaction, right? Because we're both acylating and alkylating this benzyme. The scope of the reaction, as you can see, was reasonable. There are a couple of interesting aspects to this that I want to highlight. One of them was this one. So in this case, we have a non-symmetrical arine, where we have an orthomethoxy group to that arine, and we get a single constitutional isomer as the product. Right? So that suggests that in the initial addition of the enolate, that's happening distal to the methoxy group. And we typically could explain that using a kind of inductive effect model. So if the methoxy is pulling electron density out of the benzyme, that means that the distal carbon is more electrophilic. Again, Neil Garg, who I should say is an absolutely fantastic graduate student, who's now at UCLA, with his colleague Ken Houck, they worked out a computational model for benzymes. That's a really interesting idea that benzymes are distorted in these non-symmetrical cases, and the angles that you see are different between these two, and that typically it's the carbon, the carbon that has the larger of those angles. So the more distorted carbon toward planarity is the one that's more reactive. And so they describe the reaction at that distal position as through this distortion effect. So it's probably some combination of these two, where the inductive effect is caused by, the distortion is probably caused by the inductive effect, et cetera. Anyway, however you want to explain it, we got a single product out of that. Another interesting class of compounds, again, this was Uttam's creativity, was to look at cyclic beta-ketoesters. And in a cyclic beta-ketoester, you're essentially inserting a benzene ring into this carbon-carbon bond and carrying out a ring expansion, right? So the 5-membered ring can go to the 7, the 6-membered ring can go to the 8, or the 7, 8, I don't know how many rings. This one's 8, I don't know. How big is that one? 2, 4, 6, 8, 9. Yeah, so the 7-membered ring goes to the 9. So, pretty cool kinds of products here, making these medium-sized rings, but from a small ring in this insertion process. So Uttam decided he would use this in synthesis of a different alkaloid in a completely different class, this molecule amyrancinine, and that retrosynthetically we would be making the most challenging ring, the 7-membered carbocycle, through this kind of fragment coupling ring expansion kind of process. So here's the synthesis. It just starts from this 1,3-dicarbonyl and this now decorated arine precursor. We perform that CC insertion process that builds this compound. This compound is of course, a racemic mixture. We can diastereoselectively reduce that with L-selectride to give the anti-carboxy alcohol. We then used, again, dust off an old reaction that we had developed in our lab many years ago. We used this oxidative kinetic resolution process, which employs a palladium-spardiene catalyst. So spardiene is a natural product, another alkaloid, but it's got a chiral pocket. And molecular oxygen is the terminal oxidant, and under those conditions, we actually selectively oxidize one enantiomer of a secondary alcohol in the presence of another. So one enantiomer of this racemic but diastereomerically pure compound goes on to this ketone. The other enantiomer is left behind unreacted, and that's this molecule, which we can access in 96% EE with slight overconversion. So we probably get about 42 or 43% yield of that compound, which then can be converted to amyrancinine. This other molecule, we can epimerize that center, essentially re-racemizing it and feed it back into the cycle, so we can recycle the material in the synthesis as well. So that was the use of the cyclic ring expansive kind of arine insertion reaction. But these other processes, these simple acetoalkylation linear compounds, we didn't really know what we would do with them. We didn't have a use for them. Remember, this reaction was an accident. So we thought about what we might do with them, and one of the things that we found that was quite simple to do is just treat it with ammonium hydroxide. So instead of working a reaction out, we just add ammonium hydroxide and stir that around for a while, and these dicarbonyl compounds then condense to these hydroxyisoquinoles. And that turned out to be really general as well. So we could simply do this as a one-pot reaction, where in the workup we just access the isoquinoline products here. And I'll note, again, we can take advantage of the fact that, we have this methoxy group selectivity and access, fairly complex, non-symmetrical isoquinoline units from this really simple transformation. So this really inspired us to think a lot about benzymes. We developed a whole program on benzymes. There were many students who were involved in this. And one of the interesting aspects to it is, we're thinking about how do you design a reaction around a benzyme. A benzyme is kind of a 1,2 dipolariphile. And so you need complementary polariphile to react with it. So you need something that is negatively charged. That was, in this case, the central carbon when it's deprotonated, and then something positively charged to react with it. That was the carbonyl. That was how the reaction was set up. So we designed a bunch of reactions, and we saw some beautiful benzyme chemistry the other day from Professor Da Silva Jr. I think that's how you say your name. I don't know. Anyway, some great stuff the other day. And many other people clearly have been inspired to think about benzymes, dating all the way back actually to one of my super senior heroes in chemistry, Jack Roberts at Caltech. Jack was actually the first to unequivocally identify benzyme as a reactive intermediate in synthesis, and it was great to show him about this chemistry and talk about benzymes with him. In any event, one of the reactions we were thinking about was the reaction of an arine with an acyl enamide. And so these kinds of compounds are structures that are very familiar to those who do hydrogenation chemistry. Right? These are typical asymmetric hydrogenation precursor molecules where you're hydrogenating this olefin and generating an amine stereocenter. So these are readily available compounds. We thought, if we could react them, we'd have a nucleophilic portion of this through the enamine, and then, at least one or two possible electrophilic units. We'd have the acyl group or the iminium ion. We didn't really know how that would react, but we thought these might be interesting substrates to react with benzymes. And it turned out that when we did that, we actually observed another isoquinoline synthesis. So we think in this case, it's the enamine that reacts with the arine, and that the resulting phenylanion now attacks at the acyl position of the N-acyl enamine. And then we get an elimination of water that aromatizes the system, the heteroaromatic compound. So that reaction also turned out to be quite general. So now we had a way to take these acyl enamines and append on an aromatic ring to basically make these isoquinoline units. These, again, showed exquisite regioselectivity in the cases that were non-symmetrical. So in this case, again, where we have a methoxy group, now the initial attack is, again, distal to the methoxy. And so in our isoquinoline synthesis, the methoxy group ends up proximal to the nitrogen, which is the same as it did through the acylalkylation ammonia condensation. So now we had multiple ways to make isoquinolines, and it was really at this point where we remembered that we had an interest in these compounds from some year before. Right? That some of the students who were working on the benzyme chemistry happened to be dating some of the students who were working on this project, and they started talking about what they were doing and came up with a really interesting proposal. So if I go back to the limonamycin final slide, you'll recall that I was sort of begrudgingly saying that we had completed this molecule, and I had some complaints about our synthesis. One of them was the stepwise construction of the CC bonds, right? Remember, we did a Suzuki coupling and then a Pictet-Spengler to make that key heterocyclic ring. Also, the Pictet-Spengler was really a boring reaction that everybody in the field did to make these compounds, and we wanted to do something different, but we were stuck with it. And it actually cost us a bunch of steps in the synthesis. So not only was it something we maybe didn't really want to do, but it cost us. So now we had an idea that using these isoquinolines, we would come at this from a very different way. That if we start from something that's in a higher oxidation level as the aromatic and start to reduce that down, that maybe through reduction chemistry we could access molecules of this family. And we thought that quinacarsin would be an ideal starting point for this experiment for a couple of reasons. One was that there were a number of previous total syntheses of this molecule. So whatever we did, we could benchmark against past successes, which is always, I think, good if you're coming in late to the game, and we're coming very late. As you can see, Fukuyama had made molecules of this sort decades before us. The second thing is probably now noticeable to you, which is this methoxy group, right? Quinacarson actually is one of the least decorated aromatic units of this entire class. Most of them have many more functional groups or substitutions on that aromatic ring. This only has a single methoxy group, and it's proximal to the nitrogen in the tetrahydroisoquinoline. So the design for the synthesis was really quite straightforward. We would now take an acylenamine that is now much more complicated. It's decorated with a pyrrolidine ring. React that with this non-symmetrical arine precursor, and if everything worked the way we hoped it did, we could access a molecule of this complexity through this single transformation. So in this case, we'd make both of those carbon-carbon bonds in one reaction, and we'd be set up for just reductive production of quinacarson. So that was the design. So we were going to take advantage of the same early stages of lemonomycin in this route. So the Joule-Garner cycle addition, again, functions terrifically. At this time, after step number 1, we actually separate diastereomers because we have an auxiliary, and then we treat that product with sodium methoxide, which just methanolizes the auxiliary away, and we can access the methyl ester version of our diazobicycle in 74% yield and 99% EE because we separated away the other diastereomer before we cleaved the auxiliary. So with that compound in hand, then we acylated on nitrogen, and then that sets up really an incredibly challenging methanolysis. So if you treat this compound with methanol and just about any Lewis acid, it just reverts. It deacylates. It goes back to the starting material. But we have we kind of have a rule of thumb. We have a big stock room. We shared a stock room with Bob Grubbs' group for many, many years. He had a huge number of chemicals. And many of them you could imagine were Lewis acids. So we basically started screening Lewis acids. And so in the end, for reasons that remain unknown, yttrium triflate in the presence of methanol turns out to be an ideal Lewis acid for the desired reaction, which is attack of the methanol of the internal carbonyl instead of the external carbonyl. And that leads to the ring open N-acylenamine that we need for our synthesis. That was probably the hardest step in the entire synthesis, was figuring that out. So with that compound in hand, we could then probe this arine chemistry. A reaction with our methoxy arine precursor in the presence of TBAT, just a dry fluoride source, leads to the arine annulation and produces the methoxy isoquinoline as a single constitutional isomer in 60% yield. So that reaction worked. That was really exciting. So at this stage, we have to start reducing this isoquinoline. So we started by a 1-2 reduction with palladium on carbon and hydrogen just in 1 atmosphere. That carbon-nitrogen bond reduces relatively easily. The second olefinic carbon-carbon double bond didn't reduce under those simple conditions. We treated them, though, under chemical reducing conditions of sodium cyanoborohydride and acid, and that reduced the second olefin to here. We didn't know the stereochemical outcome, though, of either of those transformations. All we knew was that we got a major diastereomer from the first step, 3.3 to 1, and then each diastereomer we took individually through led to a single diastereomer product. So whatever the stereochemistry was, the final product of each of these was a single diastereomer. So we had a 3.3 to 1 mixture of diastereomers after making both of these stereogenic centers. Okay, so to figure out which stereocenter we had, we took the major diastereomer and the minor, but the major diastereomer through our hydrogenation chemical reduction sequence and just heated it in toluene and closed. And at this stage, we were able to confirm all the stereochemistry of the molecule to be exactly the one that we needed for quinacarson. So the major diastereomer through the hydrogenation, actually we got lucky, turns out to be the diastereomer that we needed for the synthesis. And then we just complete the synthesis by converting the benzyl group to a methyl group here, debenzylating there, and reductively cyclizing to generate quinacarson. So the total synthesis here was 11 steps now, 10% total overall yield. And so compared to previous syntheses that had used Pictet-Spengler chemistry primarily, this turned out to be the shortest synthesis of those before. So the benchmark of this synthesis was successful in that way. And we think that it's primarily due to the fact that we make both of these carbon-carbon bonds in a single step. We don't make them stepwise. So that was exciting. So then we decided, we should take this one step further. right? Which was to move away from the first class of natural products, the 3,2,1 bicyclic diazobicycles, and move into the 3,3,1 diazobicyclic series that has 2 isoquinolines embedded in the core of these structures. And the reason for that was that there was a natural product called duromycin that had been isolated, some time before, but was one of the relatively newer members of this family. It comes from this sort of beautiful sea creature, kind of looks like a panda attached to something blue. I don't know, the blue scarf or something. In any event, duromycin is sort of an indicative molecule of the saccharomycin family of these molecules. So it's really related to all of these. But we like duromycin in particular because both of the peripheral rings essentially were identical. Right? And they were identical with respect to their placement to the internal nitrogens, which signaled to us there was a hidden symmetry in this molecule. And we wanted to take advantage of that symmetry in synthesis. So our retrosynthetic design was as follows. If you take duromycin and just cleave open the lactam or carbonylamine carbon-carbon bond, you unveil the amine of the isoquinoline and the carboxymethyl group out here. So the key step and key recognition was to take that molecule and simply transform it back to the heteroaromatic system, which now is a completely achiral bis isoquinoline structure. And because of the symmetry of the aromatic rings and their relative constitution to the nitrogen, meaning, for instance, there's an orthomethoxy here that's proximal to nitrogen and an orthomethoxy that's proximal to nitrogen, we thought that we could perform a double arine annihilation type process and have access to a molecule like this, which would be sort of a double enamide structure, but using the same arine. That was the entire choice behind duromycin as a target. And so we thought this would be a really interesting reaction, sort of do this in 2 directions. And then these would come back to their precursors. So we were really excited about this, but the key step for this now was really this reduction step here, right? And I want to walk through that because I think it's worth pointing out because that reduction is what kept this project going for a long time. And I'll get to some of that in a while. One thing that's, again, important to say is that the benzyne approach avoids the electrophilic aromatic substitution chemistry, the Pictet-Spengler chemistry. That will become important much, much later. But it really is a distinguishing feature to our approach relative to other approaches that are in the literature. Almost everybody uses Pictet-Spengler chemistry or some other kind of Friedel-Crafts process to build these rings, and ours really wouldn't. It fundamentally uses an orthogonal orbital set, the benzyne. Okay, so take a second on this reduction process here. Okay, so here's the bis isoquinoline. I've stripped it now of all the peripheral functionality, and here's the final compound down here. If you imagine reducing this all the way down, or fourfold. What we thought was intriguing about this is that in this particular system, you may not know which of the carbon-nitrogen bonds you might reduce, but we thought those would be more susceptible to reduction in any context than the carbon-carbon double bonds if you draw them in this fashion. So let's imagine we reduce the 1,2 bond on the left. That would go this way in our cycle. So we reduce that carbon-nitrogen double bond. And imagine that we have something that's templating this. This could be a metal. It could be a proton. We don't really know. Oops. Back to that. It could be a metal. It could be a proton. It could be something that could template this in this fashion. So let's reduce this way. Alternatively, we could reduce the D-ring carbon-nitrogen bond. That would go this way. And I'm just showing it right now, reduction from the bottom face, essentially away from the structure in the board, the alpha face. Okay, so once you have this and it's templated, we think, and we've disrupted aromaticity in either of those rings, the second most favorable double bond to reduce is the carbon-carbon double bond in the same ring. We've de-aromatized to start with, so we're going to reduce the second bond. So if we reduce this olefin and we've templated this, we think we now should have a preference for the same face hydrogenation. So we hydrogenate again from the underside. If it goes the other way, again, we would hydrogenate from the underside on that ring. So then the next the next double bond to reduce will be the second carbon-nitrogen bond, which everyone did reduce in the first case. So we'll reduce the second one, but now this thing's templated in a way that's actually, turning itself into a bent structure. So because of the templating agent, we're now forming a kind of enforced convex-concave situation. So the next hydrogenation will happen again from the same face. Doesn't matter left or right. And then the final one, it'll happen again from the same face as we go around. So although we have, free rotation ostensibly between the two rings, if we template it and start reduction in one spot, we think we would have a kind of self-reinforcing diastereoselectivity selectivity as we go through this process, this fourfold hydrogenation. That was a really intriguing idea, we thought. And now, thinking about asymmetric catalysis, all we needed to do was perform an asymmetric catalysis once. Whatever carbon-nitrogen bond goes first, if that is set with high enantioselectivity, we thought the diastereoselectivity selectivity should just follow. So that was the design behind this reduction cascade. Okay, so we wanted to try this double arine reaction, so it took us some time to build a bisenamide. We reacted it with an arine precursor, just a model system, and under our best set of conditions, this is the best we could do. This looks nothing like the structures I wanted to show you. We've made one of the isoquinolines here. The second one just arylates, it doesn't cyclize, and that compound we isolated in less than 5% yield. That was our best case. So this is not going to work, right? So back to the drawing board. The double arine reaction doesn't work. So if double doesn't work, let's do it stepwise. So same stereoselective reduction gets us back to the same compound. We're now going to exchange a carbomethoxy for a hydroxy so that we can use our other acyl alkylation condensation process. We disconnect that again by arine chemistry, goes back to a 1,3-dicarbonyl, and disconnect this by a simple arine annulation that should work. That does, we can access this material relatively easily. We can extend this out to a 1,3-dicarbonyl. Now with this isoquinoline appended on it, we perform this complex arine insertion reaction with the polysubstituted Kobayashi precursor. The insertion works, the acyl alkylation works. But then, despite our best efforts, condensation of that with ammonia never worked. Right? The dumb step at the end, the simple step in the workup, didn't work. We weren't able to access the hydroxyisoquinoline of this double isoquinoline system. So that was unfortunate. So we had to go back again to the drawing board, and ultimately I think came up with an even better retrosynthesis. And I think for those of you who do complex molecule synthesis, you may have experienced this. Your first idea seems tantalizingly exciting, but it doesn't work. Your next few ideas are usually concessions to that first one. But then at some point, your nth idea, I'm showing this as our third idea, it was probably our 12th. That nth idea is actually better than the first one, right? And that's kind of where we are with this stage. So at this point, again, we're still going to take advantage of this hydrogenation process. That was the thing that kept this project going. And it actually kept going for about 10 years. It took us to make this molecule. The key disconnection here, though, is the disconnect by a cross-coupling. So instead of worrying about doing benzyme chemistry on these complicated intermediates, we would just perform a cross-coupling reaction that would allow us to make individual monomers by our arine chemistry and then just bring these pieces together, or frankly, any other chemistry. So that was the idea. And at the time, we were also excited about thinking about, a CH functionalization type cross-coupling, because we were part of a big center in the US called the CH functionalization center that was headed out of Emory by a friend of mine, Hugh Davis. Okay, so that's the idea. And so we could build the first isoquinoline using the arine insertion chemistry and triflate that. That sets up our electrophile. The second isoquinoline, we could use the arine insertion chemistry. This time, this was actually the first example of a formamide insertion reaction or annulation process. So this is a formamide out here instead of the acetamide. So that leads to a compound that has a hydrogen here. That worked. It's not a great reaction, but it got us material. And then we oxidize that to the N-oxide because that sets up a particular kind of CH functionalization cross-coupling of pyridines and isoquinolines, and specifically that was pioneered by another friend of mine, unfortunately, the late Keith Fanyo. Oops. Uh-oh, I got tangled up. Okay, so the Fanyo cross-coupling essentially takes advantage of this N-oxidation and enables a concerted metallation deprotonation event at this center, which then undergoes a cross-coupling reaction. I'm going to move this so I don't do it again. Okay. And with these two precursors, this chemistry worked okay. We could make the carbon-carbon bond, reasonable yield. You'll notice very high palladium loadings, very high ligand loadings, but we were excited that we finally had access to a bis isoquinoline. It doesn't have everything we need on it. We had to actually oxidize this to the hydroxy methyl group here, but that was okay, and then that set up the investigation of this hydrogenation, which we were excited to look at. Okay, so our first time through, we took this molecule and treated it with hydrogen and platinum oxide, so not thinking about asymmetric catalysis, just hydrogenation. And it turns out that under those conditions, we actually per-hydrogenated the system. So both heteroaromatics hydrogenated, not with perfect diastereous selectivity, but with some level of diastereous selectivity. But in this form, it was very hard to figure out what was going on. And so just like in quinacarsin, we wanted to cyclize it, lock the system, and then we thought we could figure out the stereochemistry at that point. So we started to heat this up and started to treat it with various conditions, and nothing ever cyclized. And when it wasn't cyclizing, that of course made us think maybe it's not the right diastereomer, because there were diastereomers that you could build models of that hydrogenation product that essentially would be unable to cyclize. Luckily, though, we tried a fairly unconventional set of conditions, which was to simply treat this with lithium hydroxide. So really what we were trying to do was saponify this ester, and then we were going to try peptide coupling conditions to build that CN bond. But under the saponification conditions, the reaction actually performs and closes to the lactam. So the lactam forming was a big deal, and after we methylated that, we were able to actually then confirm stereochemically that all the relative stereochemistry of that was as shown. And so in this hydrogenation event and then cyclization, we had actually accessed the entire core of geromycin effectively through this one-step tetrahydrogenation cyclization event. That was really thrilling. Of course, it's a racemic mixture. The yields here are relatively low. And the material throughput in general was low. But the upside was that it was diastereous selective and we could access this. So that was our most advanced intermediate. And this project at this point had been going on for 3 or 4 years. And we were excited about this and thinking we were close to the end. That was in 2012. So we didn't publish this for many years after that. So we tried to improve every part of this, right? We tried, to increase the yields. We tried to increase the material throughput. All these things, everything was a problem, and it was really challenging to do so. And we were struggling at every stage with late-stage functionalization because we didn't have much material. And of course, anybody who has done a synthesis of this nature, that if you have more material, you can win. If you don't have material, you're going to lose. So we needed to do something in order to access more material. And so some years later, we made a very small but critical change. And so small you may not immediately see it, so I'll highlight it. We shifted this methoxy group from a methoxy that's on a position that's essentially inside the curvature of this ring system to the other side, to the methoxy over here that's now on the outside of that curvature. And that made all the difference in the synthesis. With that now, though, that methoxy group is distal to the nitrogen. We could no longer use our arine chemistry for that piece, but of course at this point we really didn't care that much about that, and so this would be our new N-oxide for the Fanyo coupling. That is accessed actually through an interesting reaction, which is just a silver triflate catalyzed cyclization of an alkynyl oxime. So that cyclizes directly on there and builds this, and all of this chemistry to access that could be done on large scale. And crystalline. We had crystalline intermediates. We could, do this relatively easily. The other piece, the other isoquinoline, this is shown in its, all of its entirety. We start actually from this dimethoxytoluene. We do a CH functionalization like a heart. Then we install a silyl group there. We trade out the carbamate for the triflate, and then perform the acyl alkylation process. We don't isolate the intermediate, we just treat with ammonium hydroxide and can access the hydroxyisoquinoline. That then gets triflated and sets us up for the cross-coupling. And this is really the reason why the methoxy transfer was so important. In the concerted metallation deprotonation, there's a lot happening at that position, the one position of the isoquinoline and oxide. And so with the methoxy group at the peri position, that always interfered with that chemistry and hampered its scalability, it hampered the yields. You saw the high catalyst loadings. We were able to lower the catalyst loadings, but most importantly, increase the scale. Right? So these are done on a multi-gram scale to access now this cross-coupled product in exceptional yields. This was terrific. So with this material in hand, again, we have to do some peripheral cleanup. We have to install this hydroxymethyl group. That's done actually through a second N oxide, which treatment with methyl trioxorhenium, and then treatment with acetic anhydride performs what's called a Berkelheide rearrangement. You take an N oxide to an oxidized neighboring methyl group at the 1 position, so that gets oxidized and acetylated. And eventually we can access this material through oxidation to get to the carbomethoxy group. And this then sets us up for that hydrogenation again. So just as a reminder, for the hydrogenation, now with the hydroxymethyl in place and really thinking about asymmetric catalysis, we're going to use that hydroxymethyl group as an anchoring group. That's the thing that's going to latch on to a catalyst that's going to direct the first hydrogenation to this CN double bond. We want that to be as selective and specific as possible. And then from there, we think that the catalyst should take over, that the substrate actually effects should take over beyond the catalyst, that it should just be this self-reinforcing diasteric selectivity, and then eventually cyclization onto this compound. Okay, so that was the dream. The unfortunate thing was with asymmetric hydrogenation, despite the fact there was review articles written on heteroaromatic hydrogenation reactions, the most recent one at the time, which was around that 2012 time, only had one small section, 2 small paragraphs on isoquinoline hydrogenation. So asymmetric hydrogenation of isoquinoline was relatively unknown in the field. And again, for us, this is great, because this was an area of methods development that we never would have identified without the context of multi-step synthesis. So this is really how synthesis drives methods development. We needed this target. We need the target is dictated by nature. We're making that target. We have to do this. And so we had to do something here to develop some of this chemistry. What was known, this is really the single example for asymmetric hydrogenation of a 1,3-disubstituted isoquinoline. This was done by Mashima and coworkers. And they used this pre-made iridium dimer catalyst here and can access materials of this sort. You'll notice, though, these are really unfunctionalized materials. Aryl is usually benzene with nothing much on it, and cyclohexyl is either cyclohexyl or N-hexyl, just unfunctionalized alkyl. And this was further exacerbated by the fact that actually Mashima's right-hand man was this guy Yusuke Kida. He's on both of these papers. Yusuke was a postdoc in the group right around this time, and he told us this would never work. So that was a bad omen for us. But we took some inspiration from the work from Syngenta. So they make this molecule metolachlor, which at the time was the largest industrial asymmetric hydrogenation. They do this asymmetric, in fact, the largest example of asymmetric catalysis. So they do this on greater than 10,000 tons a year using an iridium catalyst. It's a hydrogenation of a ketamine, which is not that different from the types of systems that we're interested in. So this is not using a pre-made catalyst, but they think actually the catalyst that's generated is very similar to that Mashima was using. So this seemed like a good thing for us because now we could screen ligands. And that's really important in an endeavor like this because our system is really very different than anything that's in the literature. So we started to do that. We actually started with the metolachlor conditions, xylophos, which I showed on the previous slide. We performed that reaction. And you can see about 2% conversion. Now, conversion is not to this thing. This is what we ultimately want. We don't see that at all. We actually just see 2% conversion to something that has a mass of the starting material plus 4 hydrogens. So we know we've hydrogenated something, we just don't know what. It's too little. We, bump up the temperature, we add more iodide. That seemed to be something that was shown in the literature to be important. Now we can get 30% conversion of that thing, whatever it was, and so we did a little bit more of an investigation of what that was, and it turned out it had hydrogenated the left-hand ring, the ring that was proximal to the hydroxy group. That was good. And it did so with perfect diasteric selectivity and 80% EE. That was exciting, but only 30% conversion. So now it really became an optimization effort, and we thought even if we could only hydrogenate that one ring asymmetrically, we knew that platinum oxide would hydrogenate the other ring. So we always had that as a backup. So we started looking at how to optimize this, this hydrogenation. And we used, this is what I was talking about the other day, we used our own 3CS, our Center for Catalysis and Chemical Synthesis at Caltech, which has a lot of interesting facilities and analytical equipment. In this case, we sort of did a parallel bomb system where we basically just ran hydrogenations at the same time in an autoclave setup like this. So we could do about 10 at a time in that PAR bomb, and over the course of a month we could screen 60 ligands. And in that time we could move from xylophos, which was our initial hit, 30% yield, 80% EE of the partially hydrogenated compound, to this thing, which is now a bis-trifluoromethylated phosphine derivative, which goes in 100% conversion, slightly elevated EE, 88%. So that was exciting. But what was most exciting was that using these conditions at that high level of conversion, we started to see the first traces of the desired pentacyclic product, right? The ultimate product that we wanted. And so now we were off to the races to try to optimize the formation of C. So B is the partial hydrogenation, C is the final compound. And you'll see in all of these earliest ones, we saw nothing. At that 83% yield mark, we saw 10%. We boost the temperature even further to 80 degrees, and we start to see 40% of compound C. And in the final iteration, we simply perform the reaction for 16 hours at 60 degrees. We think that that does the first hydrogenation of the first ring, sets the enantioselectivity, and then we boost the temperature for the last 24 to 80 degrees. And at that point, we see 59% yield of compound C, only 3% yield of the partial reduction product, perfect diasteric selectivity, and 88% EE. That was really exciting, I have to say. We confirmed the structure by X-ray crystal, so confirmed relative and absolute stereochemistry, so we could perform this reaction, and at the end of this, on half-gram scale, we could actually recrystallize this to an antioppurity. So we had, finally, access to material of this nature, of this complexity, in a reproducible, scalable way. So with that material in hand, to finish the synthesis, we need to peripherally decorate this molecule, right? We need to oxidize both of the rings up to the quinone systems, we need to acylate on the alcohol, and we need to partially reduce the lactam to the carbonylamine and methylate the nitrogen. That's what we needed to do, and that's what we did. We formulate and reductively methylate the nitrogen. We then perform an incredibly rapid dichlorination process. So this is N-chlorosaccharin in hexafluoroisopropanol. In 1 minute, we chlorinate both of these positions. Without hexafluoroisopropanol, this reaction takes a day. It's amazing how accelerating that reagent can be. Okay, so with this compound, we trade then the chlorides for hydroxides using a procedure that sort of combined some chemistry from Buchwald and Hartwig and used a ligand designed by Stradiato to access this bisphenol. We then reduce the lactam using this reagent that had been developed by Corey for the actinosidin synthesis. So this is really just a diethoxy aluminum dihydride. You make it by just adding ethyl acetate to lithium aluminum hydride. You make it in situ and then reduce it. That's really selective for the lactam to the carbonylamine, which we then trade out for KCN, which is a much more stable entity, the aminonitrile. We then oxidize with DDQ. That oxidizes both of these phenols to the quinone system. And then in the final steps of the synthesis, we acetylate the alcohol and then trade back the nitrile for the carbonylamine to access geromycin. This molecule on the left is another natural product named geranyomycin. That's a much more stable compound, but geromycin, was our target. That's a much less stable compound, which is indicative of these carbonylamine structures. Okay, so at the end of the day, all of this chemistry that we had been doing for decades actually finally built up into here. We have arine chemistry in there. We avoid the Pictet-Spengler chemistry, but we certainly took a lot of the lessons from the early stages. That hydrogenation, remember how hard that hydrogenation was? That actually was our first foray into any kind of hydrogenation, which we used extensively here. But the synthesis really can be broken into two main steps, right? The CH fragment coupling, and then the asymmetric hydrogenation cyclization event. And what we're doing now, and I highlighted the fact that none of this chemistry relies on the electron-rich aromatic ring, right? The cross-coupling doesn't, and the hydrogenation doesn't. And that now enables us to make molecules that have never been made before, right? Because we have control over these peripheral rings, we can imagine essentially a kind of mix and match strategy where we make anything out here. We can make larger rings, we can make expanded systems, we can make systems that are perfluorinated. We do tags on them if we want to. The cross-coupling is unaffected by any of that, as is the hydrogenation. And so we have access now to really unusual and non-natural compounds of this sort that are still exceedingly potent cell killers. And now we can also modulate the ADME PK properties, which have largely been a problem because of the phenolic and quinone groups in these molecules. So we're excited to see where this, this strategy takes us and what kinds of molecules we might be able to make. So that's where we're going. Finally, I'll just again thank all the group for their efforts, these folks for funding, and again this great institution for the invitation and the great honor to deliver this lecture. Thank you.
Take a breath. Absolutely breathtaking. Floor is open for questions. Yeah.
A wonderful talk, sir. It is a wonderful journey and complete execution. But sir, in benzene chemistry, when you deal with acid-to-acid type system, so what will be the product if someone do with malonate type system? It will be cyclobutanol type system or just substitution?
Yeah, with malonates, in our system with the Kobayashi precursor, so under fluoride basic conditions, it usually just arylates those systems. But if you generate the benzyne under very strongly basic conditions, you can get the insertion chemistry. And that actually was known, it turns out, way back into the 60s. So if you just use like chlorobenzene and LDA and a malonate, that reaction works in the same way. You get the acyl alkylation product out of that. But under the fluoride conditions, for whatever reason, that doesn't work. It only works with the ketoesters, but you can also substitute some other things. People have looked, in subsequent years, people looked at things like, I want to say like keto sulfones, I think, work, and some other ones. So there's been a number of developments there, but as far as I know, the malonates, for whatever reason, don't work.
And sir, what factor control the stereochemistry in the Pictet-Spengler reaction in case of limonamycin?
Oh, that's a good question. Yeah. I don't think I have I'm sure I don't have a drawing of that. But let's go back to that. There it is. Yeah, so, once it forms the iminium ion there, then you've got this peripheral group in this case, right? And so it's that group, I think it ends up in a pseudo-equatorial arrangement, and then an attack onto that leads to essentially the syn disposition of those two groups, right? So the sort of pseudo-equatorial nature of that causes this thing to go to the underside of that iminium ion and then alkylate. Yeah.
Yes, just outstanding talk. Yeah. I have a few questions. Let me start with benzene. So when you started the benzene chemistry, you had a methyl group at alpha position.
Yeah.
So that's why you got both annihilation as well as cut and paste chemistry. So later, you started with the cyclic beta ketase.
Yeah.
So you have
There's a group there. Yeah.
group there, but still it works. Did you make any minor change in the fluoride source or heating?
No, I don't really think so. I think it was the fact that it's cyclic, I think, helps a little bit in the sense that, because the group is tied back, it makes it a little bit more, sterically accessible. It's really, I think it's that attack on the ketone. I'll go back to this part that shows the mechanism. I think it's the attack on the ketone that is bifurcating, right? If this is an accessible pathway, you can go this way. And so when these groups are tied back together, I think it makes that ketone just a little bit more accessible. Whereas when this group is kind of free to move around and, get in the way, it can slow things down. And it allows this carbonyl to sort of move away from where it needs to be. And that, I think, is kind of what leads partially to some of this.
So then when you have methoxy group,
yeah.
So that really played a very important role in the reacher selectivity.
Yeah.
Do you think it's also because of steric reason?
There certainly can be a steric effect, right? And so that's, I guess, the third reason. Maybe I should add that to that box. So there's sterics, then there's the inductive effect, and then there's the distortion effect. So it certainly could have a steric component to it. Yeah.
And since I have done some birth reduction, a small question about the total synthesis of quinocarcine.
Yeah.
The last step you have done metal ammonia reduction.
Yeah, it's a birth reduction.
Yeah. But still you have methoxy group, and you have.
Yeah.
So did it affect?
So we've never observed birch reduction on highly electron-rich aromatic rings. We've tried, actually. There was another project where we actually wanted to do a reaction like that, and we failed because of the, I think it was a dimethoxymethyl aromatic, and it's just, I guess, just too electron-rich to get that first electron to go into. If you know any tricks how to do that, I'd love to know, because there are a number of syntheses for which we would like to do that. This one, though, we never observed that.
So in quinocarcine, you have only one methoxy.
Quinocarcine only has one, yeah, but even so, we didn't see it.
Yeah, when you want it will not work. When you don't want
it, it's Occam's razor. Inverse. Yeah. Thank you. Yeah.
That birth reduction, maybe the very recent protocol where they use diamine and sodium.
Ethylene diamine. Yeah. Didn't work. Yeah.
On that methoxy thing, I was reminded actually of your Morrison and Boyle when we first studied elimination addition mechanism by benzene. So the methoxy example. If my memory serves me correctly, even in Morrison and Boyd kind of a textbook, it was kind of discussed.
Yeah, that inductive effect. Exactly. That effect has been known, for a long time. Yeah.
Very interesting. Yeah.
Hello, sir. Great talk. Sir, in this benzene mechanism, why doesn't that nucleophile attack this ester present over there?
Sorry, can you say that? I'm having a hard time hearing you down here.
The nucleophile in the benzene mechanism, why doesn't it attack this ester group present there? And
I see. Yeah. So, well, I think the ketones just more generally, ketones are more electrophilic than esters. And so, at this stage, it attacks that ketone just because it's a more reactive entity. If you use a diketone, that also works. But, we had the question about malanates, and that may be part of the reason, right? That when you have two ester groups, this chemistry doesn't actually work under our conditioning. And, we see just aerolation on those. But I think it's just a relative reactivity thing. That, ketones are more reactive than esters. Thank you. Oh, I see. No, actually, so let me, yeah, so that slide, you know, as I was talking it through, I should have added more detail. So it's good that you asked because it's a little bit confusing. This one, right? Yeah, so yeah, so what happens in this is you treat with methyl trioxorhenium. So that actually oxidizes this one to the N oxide. So we end up with 2 N oxides to start with. Then we add acetic anhydride and stir it, right? So they both acetylate. So both of those N oxides acetylate, but this N oxide acetyl actually undergoes a rearrangement and moves the oxygen over to here. So what was the N oxide ends up here. This one, you know, it's acetylated, it doesn't work over on this position. And so at the end of the reaction, that acetyl falls off because it's unstable, because it's part of the N oxide. So we're left behind just with the N oxide that we started with. We actually were hoping that we could do both, because we eventually need this to be an ester. So we really had to oxidize that position. So we tried really hard to do a double. This reaction is called a Berkelheide rearrangement. We were trying to do a double Berkelheide rearrangement for some time, and we were never really successful. So we just do the one and then do a subsequent oxidation over here. Yeah, yeah, it's kind of a neat reaction though. Yeah. It's a good mechanism problem. You should put it on a board, you know, somewhere.
Then the granulation can be done in one pot by treating benzene precursor with beta-ketoester and ammonium acetate. I notice that you have done it in 2 separate steps.
Yeah, so it's one pot, but it's not all at the same time. So I don't know if, I feel like ammonia would probably add to benzene.
Ammonium ester would be formed if you treat beta-ketoester with ammonium acetate.
Yeah, if you preform, I guess if you could preform that, but I worry about just free ammonia attacking benzene, or hydroxide even attacking benzene as it's being formed. So I think those are, you know, that's probably why I don't think we ever tried it, but it's an interesting idea. I don't know what would happen, but.
Yeah, the other question is kinetic resolution.
Mm-hmm.
Is it possible to make it dynamic?
Oh boy, yeah, we try. I mean, that, you know, that whole project was like the first project we ever worked on, was the oxidative kinetic resolution. We tried very hard to make that a dynamic system.
Adding a racemization catalyst.
Yeah, we were never able to. In theory, you should be able to, but I think part of the problem, you know, is that oxygen being the terminal oxidant, it just limits the number of different things that you can add to the reaction to try to get it to work. We had tried for a while to use a different terminal oxidant with palladium, things like, you know, you can use like an aryl halide as a terminal oxidant for that chemistry. But then, yeah, anyway, we were never successful. It's a cool idea, but yeah, to date, haven't been successful, but we're not trying anymore.
Yeah. Okay, so yeah. Debu then.
Last.
Thanks.
I'm just wondering about your palladium catalyzed cross-coupling reaction being unusual. So can you enlighten us a little bit about your choice of palladium? You find which partner you find?
Yeah.
Why you're choosing the way you
I'll go to the good one because it shows this. So, you know, Fanyo had shown that a pyridine N oxide is a good precursor for this concerted metallation deprotonation. And the challenge with cross-couplings of pyridines especially is the 2 position is hard to metallate, right? And those metallopyridines are short-lived. They're relatively unstable. So this was his solution to it, which was to generate the N oxide, which is sort of a directing group for this position for metallation. And so you transiently make the organopalladium at that position, which then, can undergo oxidative addition with the triflate. So, in some ways, this is the nucleophile, and that's the electrophile in this sort of cross coupling. Yeah, and so he had shown also that on an unsubstituted isoquinoline N oxide that you get selective substitution at that position, this 2 position, or the 1 position, instead of at this position if there's nothing there. Ours is blocked, we don't have that problem. But it seemed like this would be a reasonable way to get to the metallated isoquinoline. We tried other ways, you can imagine trying to install like a boronic ester or a stannate or something there. Those are hard and they're not stable, even in the isoquinoline series. So this was really a great way to end up with this palladium carbon bond sort of in situ,
So yeah, but while was being remarks the oxide is the other people.
This one?
Yeah.
Yeah.
And then the
I see. Put a triflate there and have a hydrogen there. I think we were dissuaded. We've never tried it. I think we were dissuaded by that because of Fanio's original report. That he showed in the unsubstituted case it was just harder to metallate at the 3 position of the isoquinoline. So we never tried to go down that route. And I don't think we knew how to make those compounds. I guess making the H compound here is probably easy. Getting to the triflate there may or may not be easy. I guess from the lactam you could probably make it, but yeah, it's an interesting question, but it stemmed from that original report. Yeah.
It's all I'm thinking through the coordination around C-shape, because that has been a constant customer in all these reactions.
Yeah.
Is it C-shape chloride in combination with acetonitrile has some major molecular role to play, or any other chloride would have done the same thing?
It's a good question. That I would say remains a little bit of a mystery in some of our chemistry, right? So for the azoalkylation, cesium fluoride was sort of where we started, but it is true that other fluoride sources, particularly there's this one that's called TBAT, which is, it's a silicate ammonium fluoride, and that thing tends to work with most of our reactions as well. So it does work in the azoalkylation chemistry also, and we use that for some of these reactions, but and in the annulation process, that did use that. That was the optimal fluoride source there. So I don't really know if cesium is playing some special role here, but it is true that when we use it in acetonitrile. And so I think that, that could be for solubility reasons, but it could be for something else as well. So I don't really know. I think the hardest thing for me has always been to understand in this chemistry, something I didn't even mention, but go all the way back to the first slide, which is, well, in this case, it makes sense. But imagine this is hydrogen, right? So if you don't have that, why doesn't this thing, or even in this case, why doesn't this thing just deprotonate or deprotonate another one, right? Why doesn't it? I mean, it's amazing that thing doesn't just quench. It's hard to believe that there's a lifetime to it. We don't think it's concerted. We tried cases where we start from enol ethers and things and treat those with benzene. They're very slow to do a 2+2 reaction. So we do think it's anionic, and it's stepwise, but why that thing doesn't just protonate is kind of hard to imagine. But yeah.
It's not 2+2.
We don't think so. Yeah. Yeah, I mean, our only evidence for that is because we independently make an enol ether, and it doesn't spontaneously react with aronides. Yeah.
Yeah, it's a curiosity question.
Yeah.
So when you work on photosynthesis or complex molecules, at some point of time, you just say, enough, and then go to other form. When do you decide to come back? Is it because you get an organic food, or you get a new idea, or the combination of both?
Yeah, it's It is probably the combination of both. I mean, you can tell from these projects that I don't let things die easily. Particularly, in total synthesis, I think different people have a different mindset. I mean, for me, if I think about that, the first slide, we're using it as an inspiration for developing new chemistry. To me, that doesn't mean that I have to finish the molecule. Right, and so it ends up being a very meandering, long story. Most of our syntheses are that way. They take on new life forms, and then we come back to it, or whatever it is, and it ends up being a long endeavor. And I'm okay with that. I don't necessarily the speed of our getting to the finish line to me doesn't matter as much as it does, I think, to some. There's some people in our field for whom that is the most important thing, right? It's just, that's not my style. And so we often will just put things on a shelf and put it away for a time, and then we come back to it. And usually coming back to it means, yeah, we have a better idea, or somebody comes in and says, that's what I want to work on. And, that's kind of how we get back to things.
Sounds like when you want to work on a big volume, the first strategy is always exciting.
Yeah, it has to be. Yeah, the first strategy should be exciting. Yeah.
Finally complete.
Yeah.
The last strategy somehow looks better.
Yeah. 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 And so if you think about, for the final synthesis, what I showed, that last slide, that cross-coupling enables us to make lots of derivatives of these compounds and molecules that are wildly non-natural. And that, for me, is really exciting, whereas our first strategy was really only going to work for geromycin, right? And even like lemonomycin, that strategy was only directed toward lemonomycin. So I think thinking that's part of maybe how I've changed the way I approach total synthesis now, too, is that it's to some degree about the target molecule, but it's also thinking about what will my synthesis enable after I'm done, that goes beyond the target. So.
Yeah, other major problem which we normally see in water photosynthesis is when you cannot finish a molecule, the student who leaves will fill the incoming students.
Don't touch it. Yeah.
So how do you make it?
Well, so we have in our group we have a great process, which is when new students join, they very often will, instead of initiating their own brand new project, they often get affiliated with somebody else to start with. I always give them a choice, whatever you want to do, but they often want to sort of work with somebody. And then oftentimes that somebody views that as their ticket out, right? So you work together for some amount of time and then just eventually just pass it on to the next person. And so, so they have to be optimistic about it in order for that handoff to work smoothly. So we don't get a lot of bad-mouthing of projects, I think. So it's a good strategy.
Just to talk about, I was reminded of the school when you said that, you don't like projects, right? So the wise man who faces to cheat, right? That you need to believe, and then don't give up. So I think you do that obviously. Any other questions? Okay, others are not made. I have just a couple of quick ones.
Yeah.
Fantastic. Hydrogenation. Did you ever think about activating the nitrogens because it was?
Yeah, what's interesting is, so I showed the Mashima work, right? And that was when we started, was the only paper that showed a 1,3 disubstituted isoquinoline. And there's only one other asymmetric hydrogenation of an isoquinoline, and that was just a 1 substituted. And in that one, they make, I think, an acylated nitrogen. Mashima's case, they used acid to activate it, but it's amazing how much that other substitution hinders that nitrogen, right? So we tried to acylate the thing. We tried. There were some cases, earlier iterations of these 1,3 disubstituted ones, where we tried to make a salt of the thing and observe it by NMR, and we couldn't. With really strong acids, we couldn't even protonate the amine. So, that isoquinoline is much more hindered because of that double substitution. And so, by the time we got to this point, there was maybe we're activating, there is acetic acid in the reaction mixture, but we knew that we had no chance of actually acylating it. Like in pyridine cases, you can acylate the things and then do chemistry on it, but for these 1,3-disubstituted isoquinolines, you can't do any of that.
Something like a phosphate, maybe dichlorosilates. That's what I was thinking.
Yeah, I don't think they'd react. I don't think they'd react. Yeah, right, yeah. But it's essentially like a 2,6-disubstituted pyridine, right? And so if you think about those, we often use those as kind of proton sponges because they're not going to do much else. But yeah.
Okay. So we heard something remarkable in terms of talk over the last few days, and today was kind of a crowning glory, right? Absolutely fantastic. For me, it reminded me of, since you are interested in music and maths, I could clearly see both had three here. And I was reminded of a famous musician in our country, Shankar Mahadevan, who had his breathless, right? And that's exactly the feeling I had when I was coming here. Because I could not take my eyes off from the slides for the entire duration. I remember last time when I had that kind of thing.
Thanks.
So, I hope you agree with me that we witnessed something fantabulous, very, very worthy of what we associate Professor D.K. Trivedi with, passion and motivating to the core for practitioners or to be practitioners. So I hope that this lecture inspires next generation of students to take this profession and contribute to this great field of science as well. So please join me in thanking Brian for a very
Thank you, Professor Brian, for this wonderful talk.
Sure.
It was truly inspiring and amazing.
Thank you.
I thank Professor Godfrey for chairing this session. And next, I would like to request Professor Dr. Lakshmi, Ravi Shankar, and other alumni to present the memento to our guest speaker.
I gotta go back up. Hi.
Wonderful talk.
Thank you.
So research for a long time, but I enjoyed it.
Thanks so much.
Our pleasure.
Thanks. Thank you. Nice to meet you too. Thank you. Thanks.
From this wonderful talk, we come to the end of the session, and I request Professor to any questions to understand.
It's again pleasant duty to thank people who make this event possible. First and foremost, I would like to thank the entire Professor Trivedi Parivar for instituting this particular award. Office staff, support staff, quite a few of those. Beta in particular, because she was not exactly well, and then still she made sure that this event happens in a seamless manner as is her forte. For any event, she ensures that things happen, and she will be behind the scene, making sure that when you step out, things are getting placed as planned. So I would like to thank all of them. Thank all the audience for being here, and thank you, Brian, for accepting this invitation and giving a fantastic talk. If I missed out anybody inadvertently, please pardon me. It is not intentional. I thank all those who are associated in this particular event. Thank you.
So thank you everyone for attending. And currently is arranged outside, so please join us for the